Hi guys, I'm Andrew. I'm one of the TAs for the summer course that you're taking right now. What we're going to do today is talk about the content for Lab 7. That is the addition of forces. So you probably watched the video for Lab 6, and that's basically just, we're going to use some of the concepts we learned in Lab 6 to get some ideas of what happens when we have a bunch of different forces acting on an object. So what we're going to look at today then is how Newton's second law affects situations where we have multiple forces, like we saw with the free body diagrams. What Newton's second law tells us then is that the summation of all forces acting on an object is equal to that object's mass times its acceleration. So, what is the summation of all the forces? Well, that's simply just equal to one force added to another force added to however many other forces you have, and that will be your total net force. So there are situations where an object's at rest then. So that would tell us that the summation of all our forces is equal to 0, and that is for constant motion or uniform motion. What that tells us that our acceleration is 0. Okay, so what we're going to do today then, our goals for today, we're going to review vector addition. Okay. And then we will also look at what resultants tell us about vector addition and how to find those resultants. And then the next thing that we're going to do is learn how to apply vector addition to free body diagrams. And then once again, we're going to look at what those resultants for those free body diagrams tell us. So we're going to take a review. And then we're going to look at the resultants, and then we're going to apply the review and look at resultants. Okay, so let's perhaps start with the free body diagram then. So let's do a simple one. We've got a box that's just sitting on a desk, right? So the two forces that are acting here then, the first one that's easiest to sort out is going to be force due to gravity. Right? Then the next one, well, that's going to be your normal force. Now, the idea is that the box is at rest. If it's at rest, that tells us that acceleration is equal to 0. And if acceleration is equal to 0, that tells us that F equals ma is just 0. So, what that tells us then about this situation is that this force due to gravity added to the normal force should then be 0. So when we do the vector addition, we'll say the force due to gravity goes down. And then I'll go ahead and write the normal force in a different color so we can see that. Actually, you know what? We're going to keep the normal force black, and then we'll do the resultant in orange. So I'm going to write the resultant for the normal force right next to it. And then we're just going to go from where we started to where we finished, but we are also keeping in mind that these are not overlapping, they should be. So the resultant then for the two forces then is just this single point. There is no real resultant. R is equal to 0, and that's what we would expect. So then let's look at a situation where we have a box sitting on a frictionless surface that's tilted. Okay? So we once again have the same two forces that we had before. So we have the force due to gravity, and that's going to act straight down. And we will also have the normal force. Okay? So then the normal force here should go up perpendicular to the surface. Okay. So then we're going to add the forces, force 1 being Fg, force 2 being the normal force, and then we're going to find the resultant of that. So that might not necessarily be 0, so we're just going to add them up and see what happens. So add force G, the force due to gravity, to our normal force here, right? There we go. So you can see that I just kind of took this, moved it over here, added that to it as well. So the resultant is from where we start to where we finish, right? Okay, so this right here is our resultant. This is then our mass times acceleration, but we'll just call that r for now. Okay, so what does that tell us? That tells us that we have some form of acceleration going down the hill, and that's because it's frictionless, so it will just slide down. Now, what about the situation where we then include friction? If friction's involved and we don't necessarily know how long it is, right? We can then use the resultant to help us figure out what we need to include in our free body diagram in order for r to then be 0. Because a lot of times when we have a box sitting on a slant, it might not slide down, so the hardest force for us to actually figure out is the frictional force. So what I'm going to do then is I'll take this same situation and we're going to look at it with friction involved, but we're going to also try to resolve what the length of that vector would be. So this is just to get the idea of the concept going, right? So let's say we have the same situation. Force due to gravity is acting down. Normal force is acting this way. And we've been given the task of figuring out what our frictional force has to be in order to get this box to remain at rest. Well, what we'll do then is we'll draw a force due to gravity like we did before. We'll draw our normal force. And then in order for this vector sum to add up to 0, we'll then take the force due to friction and connect it from where we ended to where we started. And that will give us a total net force that is equal to 0. And this is what we want if the box is to remain still, so then we can just put this arrow right here, this vector, right here, and that tells us that that's the direction that friction would act. Now, I was doing all this without numbers, so I'm going to do one more example. We're going to throw out the free body diagram for a situation that might make sense. We're just going to go ahead and use some random values, and then we can then use some measurements with a ruler to help us sort out the rest. So let's assume we have a force acting this way, and we'll say that's force 1. Go ahead and give that a little vector addition, vector arrow. Force 1 is equal to, let's say, 6 newtons. And let's say we have force 2 acting this way. And then the magnitude of force 2, well, let's actually figure that out. If this is 6 newtons, right, and what I drew here was not the best value to have drawn out for something like that, but let's just extend this to 4. So our force 1, that is now 4 centimeters long. Okay? So now that we know that this is our equivalence statement, then we can go ahead and figure out how long, what the force is here. So this is about, we'll go ahead and extend this to 3 then, so it's a little bit easier to do the math. So we have force 2, that's equal to 3 centimeters. Okay? Well, we want to figure out what force 2 is, so we're going to need to figure out how many newtons is equal to a line that's 3 centimeters long. So with this equivalence statement, then we're going to do a conversion that we're used to already. So this is 4 centimeters and 6 newtons. All right. So that then is 3 times 6, 18 newtons, divided by 4. And then these will cancel out. So that leaves us with newtons. That's just simply going to be 4.5 newtons. Okay, so we've gone and figured out what that is. So we have 4.5 newtons for this line here. Now, if we wanted to figure out a third force that would add up to 0 for all of these, then we would just have to do a vector addition and pretty much do what we did to figure out what the distance, or what the force acting at force 2 was. So we go ahead and then, instead of adding force 2 here, let's go ahead and put in a line for force 2 that is 3 centimeters long here. And that is also parallel to that line. So we're going to just go ahead and draw this vector sum right on top of our free body diagram that we had already drawn. Okay, so then in order to figure out the resultant that we want so that we can get a zero net force, then we just draw a straight line connecting these two together. Okay, so pardon my head. We're going to just draw this line right here. There we go. Force 3. Well, we don't necessarily know what the force acting here is, but because of this equivalence statement that we already have, we'll take a measurement of how long this one is. This one's about 3.5 centimeters. 3.5 centimeters with our equivalence statement. So then we're going to do this again. 3.5 centimeters times 6 newtons, and then divided by 4 centimeters. So in the long run, that ends up to be 5.25 newtons. So that would tell us that our third force, the magnitude of it at least, is 5.25 newtons. And then that just leaves sorting out the direction, and that is just a matter of using our protractor and setting a coordinate system. Other than that, let's go ahead and look at what we discussed today. So what we discussed is just looking at Newton's second law, what that tells us about a free body diagram and all the forces acting on an object. And then we learned that if an object is at rest, its acceleration is equal to 0, and that the summation of all of its forces is equal to 0. And if an object has an acceleration, then we can sort out what direction that acceleration is based off of the vector sum. All right. If you guys have any questions, feel free to email any of the TAs you have or stop by the tutoring hours, and have a good day.